Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the third section of Chapter 18, the passive filters. In this section, we're going to talk about the second type of filters, which is the high-pass filters. As we said before, filters are widely used to give circuits such amplifiers, oscillators, and power supply circuits the required frequency characteristics. So normally we're looking at filters at frequency range, and we deal with these filters at the frequency response. The filters that we're talking about is the very basic and simple circuits, which is combined of inductors and capacitors, L's and C's, with the resistors, of course. So it is a first order filters, and as we know that the capacitors and inductors are opposing each other. So as we saw in the low pass filters, the position at which the capacitors or inductors are placed change the function of the filter. So we can use L or C to do a low pass filters, and you will see here that just changing these positions will change the low pass filters to high pass filter. In fact, as we've seen in the low pass filter, it is used to remove or attenuate the higher frequencies. It will pass only the lower frequencies. In the high pass filter, it is the opposite. It will attenuate or remove the lower frequencies, not the higher frequencies, as we will see here. Okay, again, we will look at the high pass filters similar to the low pass filters. We will look at the magnitude response, both body plot and the equations. We will discuss only first order circuits. Then we will check out the critical frequency. Then we will check the second part, which is the phase response. And we will check again the equation and body plot. Again, as we explained, the high pass filter will allow signals with higher frequencies to pass while rejecting the lower frequencies. So this range will be rejected, which is low frequency below FC, and this range will be passed. And what is this figure again? Is that how much V out we will going to get as we change the frequency. So here the voltage is very low, and it will reach the critical point, then it will keep increasing till it reaches to the Vn. So after this FC, the V out is approximated by Vn, and at the FC, the V out will be equal to 0.707 Vn, and below the FC, the V out will be very small. Again, this is the critical frequency similar to the low pass filters, and we have to remember this equation. V out is equal to 0.707 times Vn. So there will be no big addition except that this shape of the frequency is changed rather than this is so in high pass filters, these frequencies will be passed and this frequency will be stopped. In low pass filters is the opposite. This will be passed and this will be stopped. Okay, so the circuits, as we will notice here, it is just flipping between the positions of C and L, and we will figure out that it is doing the high pass filter. So using the voltage divider equation and finding out the magnitude of that V out, we can again it is similar equations. Just notice that the XC is replaced by by R over here, and for the inductor case, it is this. So here we are going to see when the frequency is too high. So when the frequency is too high, let's say that frequency reach infinity. So when frequency reach infinity, this capacitor will be changed or replaced by a short circuit. So short circuit. So in this case, the V output here will be changed or will be transferred, the V in will be transferred to the V out. And if we compare it with the case of inductor, when F goes to infinity again, now we're talking about high pass filter, the L will be changed into an open circuit, so as if this does not exist. So in this case, there will be no current over here. So here it will be I approach 0, and then the V in, because there is no voltage drop here, will be transferred to the V out. Okay, I hope this is clear for you. So just replacing the position of capacitors and resistance, the same circuit was dealt with as an out as a high pass filters rather than low pass filters. Just notice that these equations are similar, but it's not exactly the same because the XC and R is the same. So when this goes to very small amount, when this becomes very small amount, this value here, so let me use this again, and I will use another color. So in this case, when FC goes to infinity, XC will approach 0. And when XC approach 0, so there will be no XC. So this case will make V out is very close to Vn. And similarly here, when this becomes too large, when the frequency goes to infinity, XL approach becomes too large. So in this case, this will be negligible. We can neglect this. So in that scenario, similar again, V out will be approaching V in. Okay, again for the critical frequency, for either type, we can find it by setting X equals to R, whether it is XL or XC. And given that this is the relation between input and output, we can solve for FC, and using these filters, and if you plug these numbers, you will find FC is equal to this value at RC circuits and to this value at RL circuits. In this case, both the results are exactly the same as in the LPF critical frequency. Okay, now let's take another example here. I want to plot the body plot of this circuit. So first step is to decide the shape of this filter. So if you recall, this filter is a high pass filter because when the frequency goes to infinity, this becomes a short circuit. So this will transfer to here. And when we talk about high frequency goes to infinity, meaning that it is high pass filter. So frequency goes to infinity. So this is the definition of high pass filter. Anyway, so let's see what is the question. So they want us to plot the body plot, and they have defined it as a high pass filter, and we have to calculate first of all the critical frequency. So we know the shape, that it will be decaying at one side, and then it will be equal to 1. So let's see what is the critical frequency. So we need to plug these numbers into the FC equal 1 over 2 pi times RC, which is a common value. And once we plug these numbers, we will find out that this is minus 10K. Okay, now we have this figure. Let's draw in this figure the numbers. Let's use this color. So what is FC? Is 10 kilo. So this is 1 kilo. This is 10 kilo. So this is the 10 kilo. Where is the 0 point? Is this, as you can see here. This is 0 point. So let's mark this as the corner of our plot. Okay, now I want to do a minus 20 dB. So once we move by one step backward, now this is high pass filter. So we're going to the other side. I have to move 2 steps downward. So here is the second point. Again, I have to move 1 step back, and I have to go 2 steps over here. So I guess this should be fine for me. And if I connect these points, it should give me somehow the approximated lines of the figure. And this part will be flat. So this is what I expect to see. Let me check my answer. Perfect. So it is matching. And please note that the pink color or the red color is the approximated one, and the bluish color, the curve, is the exact value. Okay, now finally we reach to the phase response. So again, we're talking about first order RCRL high pass filters. And in this case, it is leading network. So the output leads the input. And at the critical frequency, the phase shift between them will be plus 45. And for both circuits, the phase diagram will be from plus 90 all the way to 0. Before it was from 0 all the way to minus 90 in low pass filter. Here it is from plus 90 to 0. And at the critical frequency, the phase shift is plus 45. And by the way, these are the equations calculating the phase shift between them. Simply the XC component divided by R, or R divided by the XL component in the case of RL circuits. Let's take another example here. This is the final example, I think. So for high pass filters shown over here, find the value of C. So XC is approximately 10 times less than R at an input frequency of 10 kilohertz. So when we say that XC is 10 times smaller than R, we can say immediately that C equal to R over 10, or 0.1 times R. And this is what we can see from here. So XC is equal 0.1 R. So if R is 680, the XC will be 68 divided by 10. Now, from there, this is Xc, and we know that Xc is equal 1 over 2 by that common equation. How to find C? We can find out the C from there. And this is not a standard point, so we have to find out what is the standard capacitance that we can pick from the market. And if we choose this standard input, if we choose the standard point, which is very close to the one that we get, we recalculate the Xc, and we find out that the Xc is 72 ohm rather than 68 ohm. Okay, now figure B or part B is asking us if a 5-volt sine wave with DC level of 10 volts is applied, what are the output voltage? So we need to calculate the magnitude and phase. Now, the input is 10 volt. The frequency is now this is the input. There is a DC input and this is AC input. So the AC input is 5 volts and the DC input is 10 volts. So what is the frequency of the AC is 10 kilohertz. Now I want to know what is the output voltage. So we know that using the equation that we do have, we can find out what is the output voltage for that frequency. And using this equation, we can find out what is the magnitude of the V out and plug these numbers in, and what is the phase of the V out and plug these numbers and find it out for us. That's it. Now, just to summarize the things that we have covered in this chapter, we have go through the body plot, and we know that for low pass and high pass filters, after or before the critical frequency, it will be minus 20 dB per decade slope, and the other side of the filter will be flat at 0 dB. And we discussed the decibel and the algorithm of base, the logarithm of base 10, and how to move from normal numbers to the logarithmic scale. Then we saw the first order low pass filters and high pass filters, and how it is formed by the circuits of RL and RC, and replacing the positions and the locations of these elements, L's and C's, will change the function of the circuits. Then the output voltage at the critical frequency is always equal to 70% of the maximum, which is the input voltage. And for the low pass filter, always the output lags the input, and at the critical frequency, the angle will be minus 45. And for the high pass filters, always the output leads the input, and at the critical frequency, the angle is plus 45. That's it. Thank you for watching, and by this we conclude chapter 18, and see you in the next chapter. Wassalamu alaikum wa rahmatullahi wa barakatuh.